Okay, so now it's 7 a.m. speaker time, 11 p.m. chairman time. I guess the rest of you are in between us. And thank you for coming to this seminar. So some announcements. And you can ask questions during the seminar. And you can either use this chat or you can just unmute yourself and ask directly. But please note that this seminar is being recorded and it will be made public in YouTube very soon. I think Daniel is very quick about that. So if you want to say something in secret, like a brilliant new idea or something, and then please wait until the end when Daniel stops recording, then you can say anything. Okay, so it is our great pleasure to have Bruno Nachtergaele in this seminar series. And of course, Bruno is very well known for his many beautiful and important contributions to the field of quantum many-body systems. And in particular, he's known as the inventor of matrix product states. Okay. And Bruno has also worked with many students and postdocs. And you can find a list in his webpage where you find the names of many wonderful researchers. I really think that it's great. Unfortunately, I'm not in this list, but okay. So today,
We still have time.
Bruno. Okay, please, Professor Nachtergaele. Okay, so
thank you, Hal.
Today, Bruno is going to tell us about gap ground state phase of lattice systems. Okay, please.
Thanks, Hal, for this too nice introduction. So, yes, I'm going to talk about gap ground state phases and their stability. And so what is new is joint work with Bob Sims and Amanda Young. I will mention work of other people as well. But this is an ongoing project with Bob and Amanda. I will say a little bit more about it just in a second, how this is going. So here is as a first outline. I will give a more detailed one a little bit further down in the talk. So I will start by saying, what gap ground state phases are and what stability of the gap and stability of the ground state phases means, why we're interested in it, and how we can go about proving such a result. And I will focus on what I would refer to as the Bravyi, Hastings, Michalakis strategy. So there are specific results that Bravyi, Hastings, and Michalakis published in 3 papers about almost a decade ago. And I will review how that goes. And I think it's something really worth knowing because you can use it in other contexts and prove nice results. And in particular, one such new result that I will mention is the stability of the bulk gap, and I will explain what that means. So it's an infinite volume result, and this is important in certain contexts. And then I have some remarks. It's mostly a to-do list. It's not that the subject is finished. There is quite a few things to do, and the to-do list is not complete, but we'll mention a few things, and we'll see how much time there is to discuss. So as I said, this is a joint work with Bob Sims and Amanda Young. And this started about 4 years ago when we had this idea that it would be good to write sort of a half review, half extension paper on the techniques that Bravyi, Hastings, Michalakis introduced and their approach to proving stability of the spectral gap. And so I bet actually that this could be done in a 65-page paper. And however, as it turned out, I lost that bet pretty badly. So as we started doing this, we wrote a first paper that introduces the basic techniques of quasi-local maps and Hastings quasi-adiabatic evolution and the automorphisms as they're defined with it. And that preprint was almost 100 pages, and it appeared last year in Journal of Mathematical Physics. So tomorrow we'll submit to the archive a preprint. Supposed to try to do this weekend, but didn't quite get around to do everything that sort of needs to be done. But it'll be done tomorrow. is a second preprint, and it's also about 90 pages. And that is the one where we discuss this proof of stability of the spectral gap using this approach in some relatively general context. So these are already two long papers, about 90 pages each. Then the result about the stability of the Bell gap, the infinite volume result, will be a shorter paper. It's a little bit different style. So there will be a third paper about that, and we're currently writing that now. It won't take very long anymore. And then there's a final installment in this that we have planned, but that we haven't really started writing yet. It's about lattice fermion systems, which of course is also a very important case with many applications. We wrote some kind of outline of it a couple of years ago, which appeared in the volume of contemporary mathematics that was put together at the occasion of QMath 13 in Atlanta. But there's been sufficient interest in lattice fermion systems that we could sort of say briefly, with the right techniques that are explained in that short paper, you can do everything that is done for quantum spin systems, you can do for fermions. But there are a few twists and a few interesting applications that I guess make it interesting to write another paper. Okay, so what are gapped ground state phases? Simply put, here the word phase refers to an open region in some space of Hamiltonians you define. Maybe it's finite range, maybe a certain decay of interactions for a certain type of system. And it's an open region, so topologically speaking, where there are no phase transitions. It's one phase. There's no phase transitions. And so the ground states, this is about ground states, they all behave qualitatively the same way, the same basic qualitative properties. And of course, to be able to use this, you have to make this a little bit more precise. And so in the physics literature, sort of a generally accepted definition was introduced by Chen, Gu, and Wen in 2011. And roughly paraphrasing it is as follows. So two Hamiltonians, H0 and H1, are in the same phase if you can find a C1 interpolation of them. So you have a parameter S, and as it varies from 0 to 1, the Hamiltonian smoothly transitions from H0 to H1. And along that curve, there is a uniform positive lower bound for the gap. The gap doesn't close. And it's the closing of the gap is associated with the quantum phase transition that would be the boundary between two gapped phases. Okay. This should happen uniformly in the system size. I mean, that's sort of the way it's to be understood. Because of course, closing of the gap really only makes sense in infinite systems, but then in infinite systems, you can't really write the Hamiltonian. But we know how to deal with that in statistical mechanics. And I'm going to use a setting that is sort of slightly simplified. There's reasons to generalize it, which I'm not going to talk about now, but I'm going to just work on Z nu. And people like to define lattices and triangulations of manifolds and things like that. And this can also be handled, but then you have to introduce some further notions and restrictions. And so we have to sort of simplify things for the purpose of the talk. And then we introduce an interaction that defines for us the Hamiltonians. So the finite volume Hamiltonians are defined by summing over possibly all finite sets, and there is an self-adjoint interaction term associated with each finite set X, and it may depend on a parameter S. For instance, if you're interpolating, a simple way would be to interpolate linearly between two interactions, and this would be a C1 way to do it, but it's important to sometimes consider other interpolations. And we will, of course, have some condition of sufficient decay of the strength of the interactions with distance. So that's the notion of a gapped phase, a gapped ground state phase. And there is a variant of it, which is also relevant, which is called a symmetry protected gapped ground state phase.
Bruno, may I ask a question?
Sure.
If I have a finite system of many interacting particles, then typically there are edge modes. even
Yes.
if in the bulk there are none. How does this
Yes.
definition handle this?
Well, it doesn't talk about it, but of course, yes, this is something that has to be taken into account, and I will refer back to it a couple of times. And in fact, there was ultimately the motivation for the new result that I will talk about at the end. But it's, of course, a good remark. You want to really prove stability of the bulk gap. And edge modes may obscure that there is a gap if you consider a finite system, and it may depend on boundary conditions how it looks. Very good remark, Yossi, but I'll discuss it. So, I was just saying there is this variant symmetry protected topological phases, which is all the same thing, except that for this whole curve of Hamiltonians, you assume that there is a certain symmetry that is present. And so this equivalence relations is now a stricter one because you want curves that remain between the family of Hamiltonians that have a certain symmetry. Okay, so an example. What better example to give than one that everybody knows about, the AKLT chain? It's a spin 1 chain, and I know you know the Hamiltonian, but here is I've written the interaction in terms of the spin matrices. It's a nearest neighbor interaction that is SU2 invariant. It has a standard high-symmetric interaction in the square of it, and this combination, as you probably know, is an orthogonal projection. It projects on the spin 2 states of the two spin 1s that live at the nearest neighbors x and x plus 1. It's a 5-dimensional projection. And so what we can do, we can construct a C1 curve of projections. So in fact, I'm going to stay within the nearest neighbor interactions. That ends up at the AKLT projections on the spin 2. And starts in P0 is an interaction that has a unique product ground state. If you take the thermodynamic limit. I'm not talking about the edge states right here, but it has the thermodynamic limit that is a unique product ground state, a trivial state. And along this curve, I have a uniform positive lower bound. And so that's something we did with Bachmann a couple of years ago, a paper in CMP 2014. And so what this means is that the AKLT chain belongs to the same phase as what is the class of models with a unique ground state that is a product state. And this is in the physics literature referred to as the trivial phase. However, to illustrate that point that symmetry protected phases are interesting in their own right and something different. In contrast, if you restrict the interpolations to go over Hamiltonian to have sufficient symmetry, and there is a beautiful paper, a PRL by Haltasaki of a couple of years ago, and there have been many developments since, but there he assumes there is one spin rotation symmetry and an additional Z2 symmetry. There can be time reversal or lattice reflections or something like that. If you consider curves that all have this symmetry, and you connect again to a Hamiltonian that has a unique product ground state, it connects to the trivial phase, then you must pass through a phase transition, a point on this curve where the gap closes, and that's done by an index argument, something that takes two values and it takes two discrete values and takes two different values, and it's continuous, and therefore it can jump as long as it's well defined, which is when there is a gap, and so therefore the gap must close. So this implies that the AKLT chain belongs to an SPT phase that is distinct from the trivial phase. So if you impose a little bit of symmetry, there is a distinction. Okay. So that's what gap phases are and symmetry protected gap phases are. And I will say more about the bulk gap, but let's first briefly discuss what we mean by stability of the spectral gap. It's essentially what you think it means, but I'm going to introduce sort of a point of view that will make it easy to state the results. So, so the first thing is that if we talk about this open region in Hamiltonian space, it means that I have many curves coming out of this any point of this gap phase. And so we really want to prove that there is stability of the spectral gap under a very wide class of perturbations. And I've called them here V lambda. I will specify what kind of classes we consider in a second. And then there's a coupling constant S. So for S equals 0, I have some Hamiltonian of a gap, maybe the AKLT chain. And then I start perturbing. And so here I have the S axis. And so initially I have a gap, the ground state, the first excited state. There's a gap gamma 0. And the way we sort of formulate stability is by taking a gamma, a size of gap that is strictly less than the gap of the unperturbed model. And then define S gamma lambda, if it's a finite system, it depends on lambda in principle, where sort of the first time is that the gap is equal to gamma. And so we have a statement then that the gap of the perturbed model, the Hamiltonian H lambda S, is at least gamma for S between smaller than this S gamma lambda. And then stability will mean that we can give a lambda independent lower bound for S lambda gamma. We may not be able to compute it so, but this S gamma lambda does not vanish as lambda goes to infinity. That's what we mean by stability of the spectral gap. Okay. So this quantity will come up all the time in our statements, and you should sort of think about this picture. It's sort of the first time the gap becomes smaller than gamma, or reaches the value gamma. Maybe I'll mention this. We don't know in general that the gap is continuous in the limit, but for finite systems, of course, it's continuous, so this is well defined. Okay, so I want to explain what I call the Bravyi Hastings Michalakis strategy. And so there's a paper in 2010 in Journal of Mathematical Physics, and then one that is basically the same result and more elegant, more concise. And these two first papers, they treat what people call commuting Hamiltonian. So it's actually a restricted case where you assume that this unperturbed model is a sum of terms that all mutually commute. It's an unusual thing for a quantum system, but it is true for the toric code model, which is the model that generated the question of proving stability in the presence of topological order, as opposed to proving stability for a model that has a classical ground state or product state or something like that. And then this restriction was lifted a couple of years later by Michalakis and Zwolak in a paper where they considered Hamiltonians that are short range, finite range, and frustration free, like the conditions will say, but the terms don't have to commute. And that requires some additional work, but they had an idea how to do that. And so that is what's in that third paper. So I will explain a little bit how this strategy worked. Not all of it is different from what other approaches to proving stability of the gap do. And in particular, we'll use the notion of relative form bounds of the perturbation with respect to the unperturbed Hamiltonian. I explained that. And that is something you see also, for instance, in the approach that Fröhlich and Pizzo recently introduced. And other, sometimes implicitly, it's also the case in other works, older works on stability of the spectral gap. Then we will talk about the spectral flow or quasi-adiabatic evolution, and a crucial condition, which is referred to as LTQO, local topological quantum order. I will explain how we formulate that. And then they will state sort of the basic results for finite systems, which is a uniform gap estimate for finite systems that you can prove using this BHM strategy. Then we will discuss the thermodynamic limit, because it's important if there's going to be phase transitions to be able to formulate it that way. Then we will talk about symmetry breaking. Then we go along with topological order. It doesn't exclude that there is also lambda order, and so we need to think about that. And we'll give another example, and time to discuss some other approaches briefly. And this will not be an exhaustive discussion, and hopefully also then talk about the stability of the Bell gap. Okay. So here is a very simple way to see that relative form bounds are sort of a general way to prove stability of the gap. And well, we start with a little lemma that something you all know, a level repulsion principle, I call it, or everybody calls it. And there's sort of a general form of it. We give a proof, and in the paper there's other proofs. And once you know what you're looking for, it's not so difficult to come up with a proof. And it says the following. So if you have a Hamiltonian, densely defined salvagent operator, and then you have a closed subspace of your Hilbert space, and you consider also that subspace and its complement. And if it's an unbounded Hamiltonian, we have to assume that the intersection of the domain of these two spaces is dense in the space. And then you assume you have an upper bound, so for the numerical range of the Hamiltonian restricted to the subspace K, and you have a lower bound for B here for the numerical range of the Hamiltonian restricted to the orthogonal complement, the complementary subspace. And suppose that A is less than B. Then the lemma says the interval AB is a gap in the spectrum of the Hamiltonian. So of course, if K would be a spectral subspace, then I mean, this is trivial. This is what it says, but this is true in general for any subspace. Another way to sort of see this or to compare it to the level repulsion you've all observed in 2x2 matrices. If you write your Hamiltonian as a 2x2 matrix, I suppose say it's bounded, then I can do this without any problem. So I have a block here that is self-adjoint, is the Hamiltonian restricted to K, and then there is B, which is the Hamiltonian on orthogonal complement. And then there are the off-diagonal blocks. So what we're saying is that if the spectrum of A is bounded above by A and the spectrum of B is bounded below by B, and A is less than B, then of course, if S is equal 0, then it follows that AB is a gap in the spectrum. But in fact, it doesn't matter what S is, there is level repulsion. The gap can only be bigger if there is an S there, whatever it is. That's sort of level repulsion. That's why we call it level repulsion principle. You can say it's a variational principle for a gap. So this is a little lemma. And with that, we can now look at what a form-bounded perturbation does to a gap and show that it can move it only sort of linearly in the strength, in the form bound. So here is this lemma about the persistence of gaps. So again, we have self-adjoint operator, and suppose you have a phi. So if it's unbounded, the phi has to be defined on the domain of H. And suppose that you have these constants, alpha and beta, such that the absolute value of phi C is bounded above by CHC with a coefficient beta, and then maybe also a term that is sort of a regular bound term with a coefficient alpha. So that's called relative form bound. Phi is form bounded by H. And so if you have that, then if H had a gap, an interval AB, then in terms of these coefficient, you will have the guarantee that H plus phi has a gap, which is a little bit smaller. So you should think of A and B as positive constants. So if alpha is 0, for instance, H is a non-negative operator. So A goes up, the lower end of the interval goes up a little bit, the right end of the interval goes down a little bit. But as long as beta is small and alpha is small enough, then there is still a gap in the Hamiltonian. And this is an optimal estimate for it. And the proof is super simple. It's just you use the bound, you look at the numerical range of H plus phi, and you upper bound it on the space that is actually the spectral subspace of the unperturbed of H, the unperturbed Hamiltonian, right? Which we know is upper bounded by A. And so you just do this, H plus phi. So my phi is bounded by beta C H psi, and then there is a term alpha. So I get 1 plus beta C H psi plus alpha t squared. And so there's an upper bound 1 plus beta A plus alpha on the subspace. And on the complementary subspace, I use the lower bound with a minus sign, and I get that there is a lower bound 1 minus beta B minus alpha on the complementary subspace. And you apply this level repulsion principle, and this becomes the constant A and B that we have in that lemma, and we have stability of the gap. Okay. So now, so if you see this, well, that seems like a plan now. We need to prove that perturbations are relatively form bounded, and we will have stability of the gap. Okay, so well, here is a result that actually shows that certain perturbations are form bounded with respect to frustration-free finite range Hamiltonians, which is going to be the Hamiltonians that we perturb. So frustration-free means that the interaction that I use to define the unperturbed model, eta here, is, maybe I will write this. So these are all non-negative terms, and the kernel of each lambda is non-zero, meaning that, so there are common eigenvectors with eigenvalue 0 of all these positive terms in the Hamiltonian. Okay, that's frustration freeness. And I'm going to assume that it's a finite range R. Okay. And then what I'm not really saying here, you can have boundary conditions. This is a finite volume Hamiltonian, maybe it's periodic boundary conditions. But also, so I need to know something about the gap of the Hamiltonian, say on cubes in the square lattice of finite sizes. So I have cubes of hypercubes of size 2n plus 1, centered at x. I call them lemma xn, and I'm going to call the gap, which is the first non-zero eigenvalue of this frustration-free Hamiltonian, gamma of n. Okay. I'm not assuming that this is uniformly bounded below. So this is one part where I answer Yossi's question. So there could be boundary modes that make this gamma n vanish as n goes to infinity. And then I consider a perturbation of the following form. So this is going to be my general form. I'm going to write it like this. It's a sum over terms phi xn, where phi xn is supported in a ball centered at x of radius n. And I can, in principle, have all kinds of ranges, but they will have to decay in a certain way, and I express this with a function gn. So gn is a function that goes to 0, and I will have to assume it goes to 0 fast enough. So in fact, I will have to assume that in the end, the ratio of gn over gamma n has a finite moment. So here is the theorem that Michalakis and Zolak had to prove to go to the non-commuting Hamiltonians. And it applies to this situation, but you need to assume that these the interaction that you use for the perturbation vanishes on the ground states of the unperturbed model. So that's kind of a strong assumption, but suppose you have that, then you have a form bound. It's very simple. In fact, there's only this coefficient beta. There's a form bound like that, and you have a formula for beta. It's given by this sum. So it's basically a moment of gn over gamma n, where gn bounds the interaction strength at distance n, and gamma n is the gap of the finite volume unperturbed Hamiltonian on a cube of side n. Okay, so typically this will vanish no faster than a power law. So this is kind of okay. It means that the interactions have to go to 0 faster than a certain power law with sufficiently high power. Okay, so this is good. So then we have a relative form bound. What I previously said about stability of the gap applies, and we are done. But of course, the issue is this condition here. This is a rather unusual condition, or it seems like a strong condition. You're saying your perturbation does not act on the ground states. And then, of course, the relative form bound is kind of logical, because if there is a non-zero contribution to the perturbation by one of these terms, it must be because our C contains an excitation with respect to the ground state, because otherwise phi would be 0. And then if it's an excitation, then there's a lower bound for it, because the Hamiltonians have a gap. And so it's not surprising you can prove something like this. You know, it's a nice proof, not entirely trivial to prove it in general, because of course these things don't commute, and excited states are not strictly local, etc. But it works. Nice theorem by Michalakis and Zolak. Okay. So, but it has this condition, and of course we want to study more general models. We want to do stability under some general class of perturbations that certainly I don't want to assume a priori that they don't act on the ground state, they don't modify the ground state. And so the next idea is to say, well, what if we find a unitary transformation, or it could be a non-singular transformation, as in the Fröhlich-Pizzo approach. Suppose I can transform my Hamiltonian. And of course, this doesn't change the spectrum. So if I'm interested in the gap doesn't change by such a transformation. And suppose I'm lucky and I can show that after transformation, I have back my same unperturbed Hamiltonian, about which I know the conditions, the gap, and so on. I have a new perturbation that depends on S, and because this unitary in general also depend on S. And then there are some remainder terms. These two here, I'm not going to say very much about. And there is a constant because in general, the ground state energy, of course, shifts. It doesn't stay where it is. But that also doesn't affect the gap, right? And what I would like is that these remainder terms, of course, are small. Here there's an estimate for it. Delta is less than S, then some little delta that vanishes as lambda goes to infinity. And the term E is less than some S times epsilon, but epsilon vanishes also as I take the thermodynamic limit. And this V is of the form that we had before, but with some new phi tilde, which now depends on S, and which satisfies this condition that on the ground state projections it vanishes. And we should also be able to prove that it's sufficient, that it's bounded, that it decays in norm as n tends to infinity by some function, which is now a different function, G tilde. So then we can apply the previous result, and we have a form bound, and everything works again in a more general context. And in fact, if you work it out, what all these constants are, it's basically that the gap of the perturbed Hamiltonian is the original gap minus S times beta original gap. And then there are these small constants that vanish as lambda goes to infinity. And you can turn that into a lower bound for S lambda, which for the moment still depends on lambda, but it's an explicit lower bound in terms of all the data that went into here. If you can do this, right? So then the question is, what is the U that we should use? And well, it is the U that is provided to you by solving the dynamics for the Hastings generator, which is Hastings called the quasi-adiabatic evolution, and we called in the paper of our spectral flow, but it's appeared in many papers since then. So I'm not going to say too much about it, except the basic properties that make it useful for the purpose here of transforming our Hamiltonians. So it is of this form. So it takes it's really here, but the V lambda that's here is really the derivative of this HS with respect to S, which here is constant, it's just a V lambda. And then it's evolved with this dynamics, and you take an integral with an L1 function that is chosen in a specific way, and I won't really take the time to discuss it here in detail. You can look in a paper with Bachmann, Michalakis, and Sims, where we discuss that in great detail. What kind of function you should take to have the properties I will explain now. So then we solve. So this is a self-adjoint, depends on S, but we can solve the Schrödinger equation in the usual way, and we get a unitary. And what this unitary does is it has two very nice properties. So it actually follows the ground state of this gapped Hamiltonian. So this parameter gamma that is smaller than the gap here appears in this choice of function. And so it's actually everything here is dependent on this choice of gamma, which I'm not putting everywhere in the notation because it gets a little bit too crowded. So if you take the projection P on the ground states at S and you evolve back with this unitary evolution, you get the ground state projection at 0. So it follows the ground state. That's one property. The other property is that it's a pretty normal type of unitary evolution that quasi-local properties. You can take the thermodynamic limit, you get the nice dynamics that has a finite Lie province and velocity. And that is proved, and that is used all over to show that if you apply it to your Hamiltonian, you get something of this form. Well, you can always write things in this form, of course. That's not the point. You take the difference with H lambda, you say write some terms, but you need these properties, right? This is non-trivial, and that's where most of the work goes. It's a bit of work. Okay. But in fact, it will not work in general. There is still another crucial condition that you need on the unperturbed model, which is called LTQO, local topological quantum order. And I will now explain what that is, and I will explain it in the way we use it in the paper we're going to put on the archive tomorrow. It's a little bit different. So it evolved also throughout the papers of Bravyi, Hastings, and Michalakis. Its formulation evolved a little bit, but I think we have now sort of a concise way to express it by using what we call the indistinguishability radius of the ground states of the unperturbed model. And they are defined with respect to a function omega that vanishes at infinity. And we will have to use a function that decays fast enough. But fix such a function, then what this is about, maybe we look at this formula first. So it's about there's two balls. So there's two radii that we are considering, K and N. And this indistinguishable radius is the upper bound for which the inequality that I'm stating here is valid. So there is a K that is a smaller radius, and I'm going to have a local observable supported in that smaller ball. And I put it in between the ground state projections associated with the larger ball. And now the ground state of these models generally is degenerate. So this is not a one-dimensional projection. But the property is that this actually is very close to the expectation in the average ground state times the projection. And the error, well, there is the size of the ball, and A and is controlled by this function, n minus k. So if the larger ball on which you have the ground states is very much larger than the support of the observable, then this is practically an identity. And so this means that, in particular, that the expectation of A in all of the ground states that you might have is the same, with an error controlled by this. You could also think about this as the dependence of boundary conditions that vanishes, if you want. And in particular, so it says that these observables cannot distinguish the different ground states. They have, if the system is sufficiently large and such that this large ball is embedded in it, A will not be able to distinguish the different ground states. And if you were to do first order perturbation theory, you would see that they don't split up the different ground states, right? That's what indistinguishability means. And so the condition that we will have is that this radius goes to infinity, so that I can let n go to infinity, and so that this goes to 0. So this becomes an identity in the thermodynamic limit. Okay, so that is the LTQO condition. Yes,
No.
Was there a question?
Could you remind us what this B lambda x n is again?
So this is the
Lowercase
ball.
one.
So this is the ball of center at x of radius n.
So
Right?
it's a real ball. Okay.
Okay,
so it's okay.
It's in the lattice, of course. And in principle, strictly speaking, it depends on the finite volume you're considering. You first do all of this in finite volume, right? Yeah.
So you're considering all the observables which lives within this ball.
Yes. So this is an arbitrary observable that lives in this ball of radius k. And
Hey,
this is
Bruno?
the projection on the ground state. Yes.
Sorry, Bruno. Does this condition mean that I should regard the ground state space as a code space?
Yes. I mean, that is the property that makes it useful in quantum information theory to encode. So it's higher dimensional. So I can code a quantum state in it, but that quantum state would not be affected by local observables, which would be an interesting property to have for quantum memory. You're exactly right. That is that property. And so the Tory code model sort of very prominently has this property. And so it actually originates from thinking about the Tory code model and why its spectral gap would be stable. But you can generalize it. Exactly right. Good remark. Okay, so that's LTQO. So then let me now formulate the the theorem summarizes the conditions that you need for stability of the gap. So I simplified it slightly, so you can absorb it. And I'm not really talking about boundary conditions in any kind of detail here, but boundary conditions are important. And it's also possible that you decide to perturb in a volume that isn't quite the entire finite volume you're considering. So in principle, there's a lambda prime n that is a subset of lambda n. But these are sort of details. So I have my frustration-free unperturbed Hamiltonian that is going to be assumed to be finite range, uniformly bounded, frustration-free. Then I will choose a sequence of finite volumes because I want to have uniformity in the size of the system, for which I have a uniform lower bound for the gap of the unperturbed Hamiltonian. So in many cases, this could be periodic boundary conditions if you have a homogeneous system, but there are other cases. You're allowed to pick a boundary conditions for this, okay? Now, gamma m is the gap of the Hamiltonian on a box of size 2m+1, the hypercube. And there, this is the open boundary conditions, and you're not allowed to choose. And there we need a lower bound on the gap that doesn't vanish faster than some power law, as the size of the box goes to infinity. Then there is this function omega that I introduced to define the indistinguishability radius. And I have to be able to take that to be also going to 0 as a power law that is large enough. And it's specified here. It's not important really for the talk. Because of course, if I make this, if I make this omega going to 0 very fast, then this radius will be smaller. And so, but on the other hand, I have to be able to take it decaying fast enough and still have this radius go to infinity. And then the perturbations I can consider they're allowed to decay as a stretched exponential. Okay, maybe it could be finite range exponential, stretched exponential. This is all covered. And otherwise, there isn't really a condition. It's just this. And then the theorem says that if these 5 conditions hold, you can pick any gamma less than the unperturbed gap, gamma 0. And there will be an S gamma, which is the largest coupling constant you can take. So you take a coupling constant S that is less than S gamma. Then the gap of this system, H lambda n perturbed with strength S, will be at least gamma. And you can actually give a formula for this, a lower bound for S gamma, which depends on the beta that we calculated after transforming. There's many steps. It's not a quick thing, but this is the summary of what you can do. That is what the Bravyi Hastings Michalakis strategy gives you. And there's many examples where all the conditions are satisfied. You have spin chains with matrix product ground states like the AKLT chain, or the toric code model, or more generally Kitai's quantum double models, or models with product ground states. Many of these conditions are absolutely trivial in that case. And you can apply the strategy and prove stability of the gap. Okay. All right. Good. So what about the thermodynamic limit? So this gives you, when you can carry out this program, it gives you a sequence of finite volumes where the gap is uniformly bounded below. Now, in this recent work of Yoshiko Ogata that is really absolutely wonderful, you study symmetry protected topological phases, and you need a gap there for the infinite system. And it's really important to consider the thermodynamic limit to precisely define these topological indices that are invariants of gap phases, SPT phases. So we are interested in the thermodynamic limit. So for the unperturbed model, this is easy for these kind of systems. This is been known for a long time how to do that. Oh, I need to charge my computer. All right. All right. So by belt gap, I'm going to mean the gap for the GNS Hamiltonian. And we discovered a few weeks ago that Haltasaki is now very familiar with GNS representations and GNS Hamiltonian and things like this. And so I conclude that everybody knows by now. So this is a Hamiltonian that represents and generates the dynamics of the system on the Hilbert space, the infinite system, right? And for this kind of system, in fact, it's known for a long time that under the conditions that we have, the unperturbed model will have a unique ground state in the thermodynamic limit. You can take any finite volume ground state, it converges to one and the same limit. You go to the GNS representation and find the GNS Hamiltonian of that unique ground state omega 0. And the uniform lower bound for the gap that we assumed will become a lower bound for the gap of that Hamiltonian. And the Hamiltonian will have a one-dimensional kernel. And so it's a positive self-zoned operator with 1, 0 eigenvector here, which is the cyclic vector of the representation, representing the ground state. So that is the unperturbed situation. And now with what we have proved for this sequence of finite systems and the uniform lower bound, we can show that this carries over to the thermodynamic limit exactly for the range where you can do this procedure. So under the same assumptions, you can pick a gamma less than gamma 0, and then there is going to be sufficiently small coupling constants so that there is a unique thermodynamic limit of the finite volume ground states, and call it omega s. And this omega s will be a pure state. It has a GNS representation with a GNS Hamiltonian that will have a gap lower bounded by gamma. And very often you see this formulated like this. So if you take the commutator with the Hamiltonian V, so this is the derivative with respect to time of the time evolution of A with A star. This is actually nothing else than a matrix, diagonal matrix element of the GNS Hamiltonian. It is bounded below by gamma times the expectation of omega s A star A, which is the norm of the vector. You take the matrix element in. So, but we can just look at this Hamiltonian, its spectrum, you will see it has a gap of order gamma. Okay, so thermodynamic limit, no problem, it goes through. You can prove exactly the same what you have for the unperturbed model for all values of s that are not too large. So now, so that's really what BHM strategy was developed for, to deal with topological order, which makes it a little bit more difficult to prove stability than, for instance, when you have a simple product ground state in the unperturbed model. But as it turns out, this strategy deals equally well with Landau order. And I'm going to explain this in the case where we have a discrete symmetry that acts locally on each of the spins, right? A local gauge symmetry, maybe spin flip or some finite rotation of the spins. Or it could also be time reversal, could be an anti-unitary actually, but anything that acts just locally on all the sides. And you can also treat translation symmetries and other lattice symmetries that may be spontaneously broken, and you can do this similarly, but it's slightly more involved. And to explain it, I take this example of local gauge symmetries. And I'm going to assume now that I have a symmetry broken situation of the unperturbed model. So that means that there are different pure ground states that actually will be mutually disjoint, which are permuted by the symmetry. So this discrete spin flip or discrete rotation goes through this different, distinct pure ground states of the infinite system. So that is the case when you have spontaneous symmetry breaking, when G is spontaneously broken. And these states, I should be able to obtain them by taking thermodynamic limits of certain ground states. So I should have projections on subspaces of finite volume ground states, so that if I take the thermodynamic limit, I get these different states omega I, that are the symmetry broken states. And this set of projections should really be a decomposition of all the other ground states. So this is the projection as before on the full ground state space. If I sum all these, the natural way to choose them, they may not be mutually orthogonal, but for large balls, I should have essentially an orthogonal decomposition. So I mean, that's what we're going to assume about the unperturbed model, right? Okay. So the modification that we have to do is to define sort of two different indistinguishability radii to express LTQO, because now we are not going to have LTQO in general. There will be an order parameter for this lambda order that does distinguish between the different symmetry broken states. And so it's not possible that we have LTQO for all local observables. But we will still have it for symmetric observables. So AG are the observables that commute with the symmetry. So it's definitely not the order parameter, but anything that is symmetric under G should still have this LTQO property with a certain decay function, omega, as before. So this is the projection on all the ground states, but the A's now are only the ones that commute with the symmetry. And then there is another one, a G broken indistinguishability radius, where I can take arbitrary observables. But now I switched in between the projections that are on one of the pure ground states. So they're also multidimensional projections in general. But if I take two different ones, if I is different from J, then basically they should be zero. They become mutually orthogonal. And if they are the same, then I have the property as before, but with the pure state omega I. In principle, that this will give you a different indistinguishability radius, but there will be a similar condition. So the condition I had before, that this goes to infinity, now I have a condition that both of them has to go to infinity. That's sufficiently fast. For an omega that is going to zero sufficiently fast. And then we have this theorem of stability of discrete symmetry breaking. And it's really everything you would expect under exactly the same conditions where I have replaced 4 by 4 prime. Now I have these two indistinguishability radii. And otherwise they are the same conditions. What you're going to find is that under perturbation, the symmetry breaking that you observe in the unperturbed model is exactly still of the same type present in the perturbations. And each of the pure states, so you have a simplex of ground states, and each of the pure states, each of the extreme points have a GNS Hamiltonian. We have a gap that is still lower bounded by the same lower bound gamma. Okay, so that is stability of discrete symmetry breaking. Time for another example. I apologize, I didn't have time to really make a nice figure, so you have my artwork here to look at. There's a lot of information about these so-called ON spin chains, and but I will point to the relevant part. Let me first say what the ON spin chain is. So it's a generalization of the AKLT chain. So for n equal 3, it's the O3 chain is actually the AKLT chain, where we have O3 spins, which are the spin ones, which and we have a Hamiltonian that is invariant under rotation. So you can generalize this to n-dimensional spins. And there's many ways to write it, and in the literature it appears in various ways. And it's basically a linear combination of two terms, and one is the swap operator, which takes the states of two nearest neighbors, which of course is invariant under ON, that commutes with simultaneous rotation of these ON spins. And the other one is a projection on this particular vector. It's the maximally entangled symmetric vector. If you think about it for a second, this vector is invariant under simultaneous ON transformation. So I didn't specify the basis that I used here because, in fact, this vector is independent of the basis. Okay, so this is the ON chain. And it turns out that its phase diagram depends on whether n is even or odd. So if n is odd, it's similar to the AKLT chain. And so this red point here, maybe I should write it, corresponds to the tangent of phi is equal to n minus 2 over n. For n equal 3, it's 1/3. This is the AKLT point. But there is for all odd n's, there is such a point, and there you have a frustration-free model with a unique MPS matrix product ground state and a gap, and the conditions of stability are satisfied. So we have this yellow region here where you have the Haldane phase in that case. And for even n, you also have a special point. It's frustration-free, but you have two matrix product ground states that break the translation invariance, and there's dimerization. But in fact, with the discrete symmetry breaking, we can show that that's also a stable situation. And so there is actually a phase there that shows you dimerization. Well, there's all kinds of other interesting things to say about this model, and there's actually another dimerized phase that was recently proved to exist for all n3 and larger in a very beautiful paper by Eisenman, Domenico Pan, Simone Warzel. And we are in the process of writing a paper to show that for large n, this is also a stable phase. Okay, there isn't much more time to say about this. Maybe very quickly comparison to other approaches. I think it's part of the point I want to make. I think this Bravyi Hastings Michalakis strategy is a really good one. I won't be able to do justice to the works I mentioned, and then there's many other works that I'm not mentioning. So the older, I mean, it's not totally fair, but it's more or less correct that the older results all study quantum perturbations of classical models. And there's very interesting, beautiful work there. More recently, there was this Lee-Schwinger block diagonalization method introduced by Fröhlich and Pizzo, which handles only unperturbed models that are on site and so have a unique product ground state. But they have some other advantages. You can treat unbounded Hamiltonians. You can prove analyticity of the ground state energy and things like that. But it doesn't apply to a lot of models. In particular, you don't have topological order. So there was also work on specifically spin chains with matrix product ground state. The first proof of stability of the AKLT point was by Jarotsky, and this was generalized by Zehr and Wolf about 10 years later. That's in one dimension. And then the multidimensional analog of that is models with tensor product states. And there is a stability theorem for that too, but that is limited to perturbing the tensors, not the Hamiltonians. So sort of it's clear to me that BHM really handles a much broader class, and it's really the better approach for this kind of question. You can do multidimensional models, you can treat topological order, you can have discrete symmetry breaking at the same time, and you can also handle gapless boundary modes. So this is my last bit, and that's a good thing because there's only 4 minutes left, Hall's timer tells me. And this is the stability of the bulk gap. So, I'm going to sort of describe this in analogy with everything we discussed before. So what we had before was a finite volume frustration-free model that had a gap. And we had to assume that for suitable boundary conditions, this gap was uniformly bounded for the sequence. But as Yossi pointed out, very often you have gapless boundary modes. And so there are some explicit models where, you know, if you put it on a torus, you put the periodic boundary conditions, then these boundary modes disappear because there's no boundary. And then you can apply the strategy. Well, you still have to assume that these boundary modes in energy don't vanish faster than some power law, but that's usually the case. In some cases, there's classes for which you can prove that it has to be the case. But what happens if you don't know? Maybe it's not a translation invariant model at all. It's defined on some triangulation of a manifold, and so maybe you don't know boundary conditions that produce the uniform gap that remove the boundary modes. Or there are some papers that suggest that there may be models where there's no way of getting rid of boundary modes. So maybe these boundary conditions are not known to exist or even known not to exist. So what do you do then? Well, so what we proposed, and it works beautifully, is to use the infinite system as its own boundary condition, the infinite unperturbed system as its own boundary condition. And so we assume that that has a gap. And I don't know how you proved it. It doesn't matter. But we assume that we have this unperturbed model and the thermodynamic limit. I go to the GNS representation of the GNS Hamiltonian, and I have a gap in the spectrum. We call that the bulk gap. And then in the GNS representation now, we're going to replace this finite volume frustration-free Hamiltonian with the GNS Hamiltonian, which we know has a gap. And we perturb as before, but in the representation. So, I mean, you wouldn't be writing this all the time, but to make it clear what we're doing here, I'm writing it. So this acts on a different Hilbert space, but it's just a representation of the same type of perturbations that you would use otherwise. And you can apply the BHM strategy to the sequence. And so there is only one difference. So here again were the 5 conditions that we had. And now I'm going to assume the same conditions except this condition 2, which was a gap of the sequence of finite volume unperturbed Hamiltonians, are replaced just by the condition that the GNS Hamiltonian of the unperturbed model has a gap. And then everything is the same. You can show that there will be uniform gap in the thermodynamic limit of these perturbed Hamiltonians, and their GNS Hamiltonians will have a gap, and it will be lower bounded exactly as before for a range of S's that is even a little bit simpler because we have gotten rid of some of these correction terms, delta and E. There's the epsilons and the deltas are gone. So the GNS Hamiltonian for the perturbed state has a gap greater than gamma under the same conditions as we had before. Okay, so 1 minute left to show you my to-do list. Or it may just as well be your to-do list. It's not reserved. So all these initial models for which perturbation theory was developed, this is also true for the previous or the other methods. But it doesn't necessarily state it explicitly, but something's very obvious. You need this frustration-free property of the unperturbed model, and physically it really shouldn't be needed. And in fact, since we proved that so many models are stable, you move away from, you do a little perturbation, it's no longer a frustration-free model, right? And we showed the gap is stable. So sort of we already showed that in some sense, frustration-free should not be needed, but we can't really prove anything unless we have one reference point that is frustration-free. And physicists believe that there are always such reference points nearby, but okay, that's definitely not proved in higher dimensions. In one dimension, it is almost proved. In higher dimensions, not so. So then, so that's something that, you know, hopefully someone will work on. Unbounded Hamiltonians is another case. So as I mentioned, the Fröhlich-Pizzo method does allow you to have non-interacting system, maybe a quantum rotor type model where you have an unbounded Hamiltonian and everything works the same way. We don't have a BHM approach worked out for that case, but I think it should be possible. There's of course the unspoken issue that for the unperturbed model, for which you have to prove there is a gap, there's actually not that many examples where we can do this in higher dimensions. In one dimension, it is for frustration-free models, there's a general approach that works very well. In higher dimension, there's only a few models for which we know how to do this. So this is sort of a separate problem. This is not about stability. This is about proving for special models that you have a spectral gap, and there's still many interesting things to do there. I've assumed this LTKO condition. So it's for the toric code model, it's very easy to see. For all quantum spin chains with a finite number of matrix product form ground states, you can prove it in general. That's in an appendix of the preprint that will appear tomorrow. Will be submitted tomorrow, will appear later this week. But for higher dimensional systems, it's again not such an easy thing to do, right? So, and it's an essential condition. It's not something you can fudge a lot with, I think. And finally, there's a sort of acute question I want to stop with because my time is up. The timer disappeared. That's nice. So now I don't know how much time I've. Okay, so this is about the continuity of their gap. So we believe that when the gap is positive, you have some interval where the gap is lower bounded. It should be continuous in this parameter, the smooth parameter. And in the paper that appeared last year, we proved that it's upper semi-continuous. And so I think it should be continuous, so, but I don't know what the argument would be. Okay, I really have to stop. Thank you very much.
Well, thank you, Bruno. This was a really beautiful lecture. I learned a lot. This was a long 1 hour. Okay, so any questions or comments?
I have a question, Jan Derezinski.
Yes, yeah.
What are parent Hamiltonians?
Okay, so this is a tensor network language speak. So I mentioned this here. So so you can, in the case of one dimension, they are matrix product states. And there is a general constructions that tell you that such states are always the ground states of a finite range interaction, of a finite range Hamiltonian. And this Hamiltonian is, if it's one that is gapped, the one that generically it will be gapped, it's called the parent Hamiltonian by this community of people. And so, and this has also generalization to higher dimension. So the AKLT Hamiltonian is a parent Hamiltonian of the AKLT ground state. But you could modify it. Yes.
Is this parent unique?
No, obviously not, right? Because the only thing that matters is the kernel of the interaction that makes the Hamiltonian. And you, as long as you keep the kernel, the AKLT states, it will be a parent Hamiltonian.
Okay,
so any nearest neighbor interaction that is positive and has a kernel equal to the ground states of the AKLT on two sides will be a parent Hamiltonian for the AKLT chain.
And another question. Can you summarize in one sentence the BHM strategy? Is it the use of Hastings operator, which is crucial, or something?
Yes. So the unique thing, if you want, is that you use this particular unitary to do this. So there's other constructions. As I said, the Fröhlich-Pizzo method is also through constructing an invertible transformation, which applied to the Hamiltonian turns into something that has a form bound. But yes, I would say that the specific thing is that you use, I mean, it's not quite unique. There's different choices you can make for this W, but you use this kind of generator to produce the unitary. That is what I would call, and also the identification as the LTQO property as a crucial condition. It certainly should be attributed to Bravyi, Hastings, and Michalakis.
So is it so recent? I mean, you mentioned Hastings 2004. So this is really quite recent.
So this is the paper where he gave the first multi-dimensional Lipschutz-Maris theorem. And I mean, there's quite a few papers, so, and there's different versions of it that appear in different papers. But and Hastings himself also often refers to a paper a little bit later by him together with Wen, where he introduces this. And so, so there were no precursors to this, I can't say. I mean, most likely there were, because studying expressions like this is not, that doesn't come out of the blue. But the choice of this function, which is designed, taking into account the gap of the Hamiltonian that you are studying, so that you not only have this property, but also, this is a fast decaying function, but also that you have locality. So I think actually the most important thing, the newest thing, is the idea of using Lieb-Robinson bounds to exploit locality properties. So making sure that the transformations you use have good locality properties and using those in combination with this unity transformation. That I think are the crucial ideas that I would say.
Thank you.
Any other questions, comments? Yeah, I have some questions, of course. First of all, this is an easy one. So as for two-dimensional AKLT model, like hexagonal model, that is, they have sort of proof, almost proof, for the existence of gap for finite system. So if you assume that is okay, then this applies to.
So then you still have to check the
open
LTO condition, the indistinguishability.
Oh, okay, okay.
Which in fact, you know, the way you, in your paper with Elliot and Tom, you develop this polymer expansion technique, which presumably you could use. And I think people are looking at it. So so we may have a proof soon that actually you do have LTQO. Then the gap, as you know, needs some computer assisted.
Right. Okay, so that will be the most difficult part. So this gap for open boundary is something come for free. Is it true? Or?
Well, so in these models, so you have a highly degenerate ground state. And so,
Mm-hmm.
so there's sort of boundary modes, but they are all exactly zero energy.
Right. Mm-hmm.
And so you don't have to, but you could also do periodic boundary conditions, and
Mm-hmm.
then you have a
Mm-hmm.
unique ground state.
Okay.
In
So
that
the
case.
most
But
difficult
generically,
part,
that's not the case. Mm-hmm.
Okay.
Can I make a comment?
Sure.
So first, thank you for a beautiful lecture. I think that I learned a lot here, and it was very clear. Initially, I've been confused a bit by this discussion of gap for the points which also Yossi brought up, which is in finite system, you can reduce gap by bound manipulations of the boundary conditions. But if I understand correctly, the LTQ condition is really essential. So somehow the discussion of just gap is a bit misleading. It's the LTQ condition plays an essential role in making sense of what you mean by gap in the bulk. And I'm reminded a bit, the strategy reminds me a bit of Dobrushin's approach to critical phenomena, to exponential decay of correlations, the high temperature phase. And some time ago, we tried to, with Elliot, to think about quantum version of the Dobrushin approach, and to some extent what you described captures some of it. I think
it has that same flavor. I agree. That there is a fast decaying influence of boundary conditions in this ground state that is crucial to have the stability of the gap. I mean, it's not true that gaps are always stable, right? And it's certainly, and it's not true that, so you can have isolated points in a parameterized Hamiltonian where you have a gap and you go away and the gap vanishes. So the gap is not continuous in general. It's not stable in general.
But you managed to formulate the notion of a gap for the bulk gap, for the bulk state.
So that is the one that really expresses the finite energy of bulk excitations. And it's also what Yoshiko Ogata needs to define her index and so on. So I think it is the right thing to look at.
Oh, wait. Do you have an example of a gapped system which is unstable?
Yes. So if you take the spin 3/2 AKLT chain, so you take instead of putting the spin 3/2 AKLT model in the honeycomb, you put it just on the one-dimensional lattice. Then it has a highly degenerate ground state. And actually proved in an old paper, you can do a perturbation, and create a gap, you create a band of excitation.
Right.
So you're not going to find in the literature a mathematical proof that it's gapped, but the Knabe approach works well, and you don't have to calculate a big system. So it's certainly gapped, but it's not a stable gap.
You apply infinitesimal magnetic field and then.
Right, something like that. Correct.
Any other questions, comments?
Well, coming to this model which you just discussed, which is presented, the AKLT on the honeycomb.
Oh, yes.
Does the dimension play an essential role for that? I mean,
well, yes, in the sense that it is expected. Actually, it's I think conjectured in the original AKLT paper in CMP that if you define this model on a lattice with sufficiently high degree, then you may have an ordered ground state. I mean, there's no proof of that as far as I know. We studied this on trees, on beta lattice to sort of get an idea of that. And there's already an analysis of that also in the AKLT paper. So if the degree of the vertices is 4, it seems like to be a critical case. If it's 5 or larger, there's sort of an indication that you should expect Néel order, in fact, for the AKLT model.
But we must be in 3 or higher dimension.
So, okay, well then there's the other thing. But so in this sense, yes, it does depend on the lattice, and it does depend on the dimension.
Yeah.
But yeah, it's as I said, it's one of the to-do things. So for the honeycomb lattice, we have an almost proof, as Hal mentioned. If you're willing to do some numerics, there is a way to show that there is going to be a gap for that model. It's it's a bit annoying because you have to do numerics for sufficiently large finite systems so that you can't really say we are sure. It depends on how you feel about certain numerical methods.
Any questions? So I have a physics question. So you treated these models with stable gap, and the examples are basically classified into three classes: trivial ones, which is just an independent thing perturbed a little bit, and also discrete symmetry breaking case, discrete SSB, and those with LTQO. So am I right? So do you think that these are the only cases we have stable gap, or are we still missing something?
Well, but LTQ is not one thing. So the different kinds of topological order can be distinguished. So there are definitely distinct stable gapped phases where you have topological order of a different kind. And if you want to connect them, you need to go to a phase transition. So in this sense, it's not really, I mean, it's three classes, but it's not like
okay. Yeah, of course. Yeah.
And also then, as we showed, the discrete symmetry breaking can be accompanied by topological order. They are not mutually exclusive. They can go together.
Yeah. Anyway, the question is whether we are still missing something important, or we have basically covered everything physically.
So, I mean, one concrete way, well, so for instance, in 2 dimensions, there's a very interesting dimension to think about. Some people believe that the models constructed with tensor network states exemplify all possibilities. So if that's true, then you're right too. But this has not been proved. But in a certain sense, as it is in 1 dimension, if there's something similar in 2 dimensions with tensor network states, then yeah, that would cover essentially everything. But I don't know whether that is correct. Sometimes we start believing things that if sufficiently many people have sufficiently poor imagination to think of something else, and then we say, that must be true because nobody can think of something else. But I'm not sure that's a proof.
Okay. Any other questions?
Yeah,
Comments?
can I ask about the topological order condition? Does your condition combine the 2 conditions from the original Bravyi, Hastings, Michalakis paper?
Right. In fact, it's closest to the version that appears in the Michalakis-Volak paper, which does combine them. And you can derive properties. So what I said, for instance, that the expectations in all different ground states are close and things like this. You can derive this from this condition. So yes, it's all combined in one condition. That's good.
Okay, thanks.
Very good. Anything else? Okay, if not, let's thank Bruno again. Thank you very much.
Well, thanks for coming.
And Daniel.